Hey gang, welcome back. Okay, so this is our last video in the NMR series, and we're just going to practice. 3 times to be exact. So I got 3 examples for you. Again, like I said, the best way to get good at NMR is to do a ton of NMR problems. We can only do so many together, but when the rubber hits the road, I can give you the tools and like a procedure to do it, to go about solving them, but it's going to come down to, you guys getting your hands dirty, doing a lot of problems, figuring out where your own pitfalls are, and then getting comfortable. But I think the 3 I have kind of illustrate interesting, commonly seen things, so we'll just give it a go. Alright, so this spectrum looks a little busy, and we have our formula, so let's get cracking. So remember, very first thing we do is degrees of unsaturation. Now, I've been doing the formula, but remember in the simple case where we either have halogens or oxygens. So this is the way I would do it. I don't really use the formula all that much, unless I have nitrogens involved, because they get a little interesting. So what I would do here is I would look at this formula. Remember, for oxygens, we just ignore them. I would look at C7H14. I would compare this to what this 7-carbon alkane, or 7-carbon hydrocarbon should have as far as hydrogens if it was completely saturated. So usually, if I have 7 carbons, right, I should have. So this is my N. My 2N plus 2 would be 16. So you see, I'm 2 hydrogens short, and I know a degree of unsaturation gets rid of 2 hydrogens. So right here, I can tell because I'm not C7H16O2. I actually have 1 degree of unsaturation because I'm missing 2 hydrogens from my completely saturated form. Okay, so this is important. Okay, so from here on out, let's go about our process. We are going to, I'm actually going to grab another red marker because that one kind of just died on me. Sorry, new red marker. Okay, so let's make our chart. So what we're going to do is I'm going to assign A, B, C, D, E. We have 5 unique signals. So that means, we might have some symmetry, but we technically have 5 unique positions. Oh, hold on, I actually made a mistake. This actually needs to be, sorry, just realized this. Now this is a 6. There we go, okay, cool. Just realized I picked up the bad red marker for that. Anyways, so this is what we have going on here. So we've assigned our peaks, and let's just go ahead and build it. A, B, C, D, and E. Okay? So remember, if we're going to build our chart, I'm just going to do this in black across. And again, if you like to build your chart differently than I do, go for it. So you're the master of your own NMR destiny. So first, I'm going to do the coupling, then the integration number, and then N, the number of neighbors, and then kind of like the appearance column, how we initially think it might look like, and then the one I forgot to do the first time I showed you this, but the chemical shift, the lowercase delta. Okay, so let's go with A. A is a 1, 2, 3, 4, 5, 6, 7. A is a septet, which means, and the integration is a 1, and if we do N plus 1, and we got a septet, which is 7, we have 6 neighbors. So our appearance is going to look something like this. I have 1 hydrogen at that location. I'm going to have 6 neighbors on either side, but see how A is really downfield, really de-shielded? There must be something, some heteroatom, an atom not carbon, that's more electronegative. It could be one of these oxygens. And if you looked at a chemical shift table, which you should always have handy, there's probably going to be some oxygen near A. I have a funny feeling. And I also know the answer, but that's besides the point. Okay, chemical shift. This is not an exact drawing. No Michelangelo, no Picasso. So it's going to be somewhere like, 4.5, 4.6. Doesn't totally matter if you get this precise from the chart, or from the spectrum. All right, moving on. B. So B is a triplet. Okay. The integration is 2. We also happen to have 2 neighbors because 2 N plus 1 should be 3 because of the triplet, so 2 neighbors. So we are going to have 2 hydrogens on this carbon because of the integration. And we're going to have 2 neighbors in total, and we are a little bit downfield. So if you were to, again, look at your chemical shift chart, and due to the fact, sorry, I had to do a little rearranging and erasing, but we do have 1 degree of unsaturation, we have, a little bit to play with. And what would match up super well with this chemical shift of about 2.2 is a carbonyl next door. So let's come back to this. Again, this is an initial guess, right? This is just something we feel might be the case. Whatever, yada, yada, yada. Okay, C. C is a 1, 2, 3, 4, 5, 6. C is a sextet. 6, right? Integration of 2. And as far as neighbors, since n plus 1 was 6, that's how we got the sextet, the n is 5. And C is nothing special as far as, like, it's not super downfield, right? It's, close to 1. It's probably just going to, have 2 hydrogens at this location, as well as its 5 neighbors. So we're just going to do something like that, probably in the middle of a chain somewhere. And I don't know, it's probably like a 1.5 or something like that. Okay, D. D is a doublet, and it has an integration of 6. So this is going to probably apply to more than 1 carbon. And since it's a doublet, that means we have 1 neighbor, right? Because n plus 1 needs to be 2 for the doublet, which means n is 1. And if you think about it, right, it's very close to 1. It's like a 1.2. This is probably just 2 methyl groups, terminal methyl groups, right? So I'm going to guess by saying it looks a little bit like that right there. Okay, so E. E is a triplet. And I hope you're looking at that saying you think that's familiar looking, because this is your classic methyl group. Right, integration of 3. The number of neighbors is just going to be 2, because it's a triplet. N plus 1 has to be 3, 2, n is a 2. And it's just going to be exactly what we drew above. It's going to look just like that. And I don't know, this happens to be 0.9. Again, I did not do the NMR. This is the spectrum we were given. Okay, so let's push this information all together. So sometimes it just helps to start drawing some stuff and seeing if you can match up what you're drawing to the spectrum. Okay, or sorry, to like your chart. So I'm going to start with E. I'm going to just start picking N, because I think D and E are my 2 N's, and we'll see where we go from there. So if I draw 2 carbons, right, this is going to be E. Just very upfield, no, electronegativity thing, anything like that going on. But I have to have 2 neighbors. So if I have this carbon right here have 2 hydrogens, let me just kind of extend my chain, but I'm not really paying attention to this. So can I locate what this carbon might be? This will be E. So if I look for an integration of 2, right, because that's 2 hydrogens, I really have B or C as my options. Now, let's think chemical shift-wise. If this is going to be middle of the chain, I haven't drawn any oxygens or anything, C could be a good fit, right? Because it's a 1.5, right? There's no oxygens or anything. So if I call this to be C, let's continue to draw the train, see what we can, make out from there. If this is going to be C, right, it needs to have 5 neighbors. Well, if those are 3 of my 5, and I continue the chain, I could have 2 hydrogens right there. C would then have 1, 2, 3, 4, 5 neighbors. So that works. Now let's kind of figure out this position's story. So again, integration of 2. So if I've used E and I've used C, and at any point, right, this could all be trashed and you have to restart. But so if I use B now, I need a triplet. So I need to have 2 neighbors. And you see, I already have my 2 neighbors. So you might be thinking, oh crap, I might be out of luck. However, note that B has a bit of a high chemical shift. And remember, we guessed that this could be a carbonyl, or next to a carbonyl rather. So we have not used our degree of unsaturation yet. So if I plot this carbonyl right there, not only do I eliminate the degree of unsaturation, and I found it where it is, but I've also now used B because it only has 2 neighbors, because there are no hydrogens on that carbonyl carbon. Okay, cool. So I've used 4 carbons, 1, 2, 3, 4, and I have 3 more carbons, and I have 1 more oxygen. Okay, so let's finish this off. So we've kind of established that D is going to be 2 methyl groups on the end, but they both need to have 1 neighbor. So maybe we could do something like this. There are 3 hydrogens here, right? This is just an initial guess. That would give us 1 H right there. That would give us these guys being doublets because they have one neighbor. These are symmetric. That's why they're going to be on the same peak with that integration number of 6. And then we have this carbon right here having 6 neighbors because it's a septet. However, we then note, because that would take care of D, that doesn't really handle our chemical shift of 4.5. However, right, we didn't use our oxygen, and we initially guessed that A should kind of be near an oxygen. So instead of this being a ketone, all we need to do is make this an ester, and everything we said before was fine, right? I still have my hydrogen, 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 and then the one lonely hydrogen. So here's A, and then there are both D's. Okay, gang. Oh, and this was a B. So, obviously I knew the answer, but you can go through this type of process and just check yourself. That's why it's so nice to have everything laid out in the chart, because the chart is your source of truth. This tells you everything, but it's nice to see it all laid out in a logical format that you can understand, which is why if you like to organize the chart differently, by all means, please do that. Okay, this was actually a question on my Organic 1 final in 2013, which seems like forever ago, but if you can kind of handle and dissect this spectrum, get this chart and deduce this structure, you're already in good shape. Okay, I have 2 more problems, and then we'll call it a video, a series, a wrap. Okay, so this problem is going to be a little bit different from ones that, NMR problems you may encounter when you're first starting out your career, but I wanted to show you this for, symmetry purposes as well as getting you some exposure to other things as well. Okay, so we're extremely downfield just upon glancing at our spectrum, but no fear, let's trust our process and get after it. Okay, so let's, figure out our degrees of unsaturation. So we don't have to really apply the formula here because we don't have too much going on as far as, non-carbon, non-hydrogen atoms. So let me look at what I should be if I was fully saturated. I would be Cn and H2n plus 2, which would lead me, 12 times 2, 24 plus 2 is 26. So let me look at the hydrogens I should have versus the ones I do have. I can see that I'm missing 16 hydrogens, and if I divide that by 2, right, because 1 degree of unsaturation eliminates 2 hydrogens, I have a whopping 8 degrees of unsaturation, so quite a bit. Now the reason why I picked this problem is to show you that whenever you have 4 or more degrees of unsaturation, and you have chemical shift values between 7 and 8, right? If you looked at your chart, you see a lot of you can locate a benzylic H, a benzylic proton, right? Hydrogen, whatever. So, remember that a degree of unsaturation is a pi bond or it's a ring, right? Well, take benzene, for example. It's a combination of both. And in fact, because we have 3 pi bonds and 1 ring, that is a whopping 4 degrees of unsaturation. So, we have 8 degrees of unsaturation, and paired with the fact that we have 3, signals on our spectrum, meaning all 10 hydrogens are represented by 3 unique positions, right? We're going to have some symmetry involved. And if we had 2 benzene rings, we'd have 8 degrees of unsaturation, and the fact that our chemical shift values lie in this region of the benzylic realm of possibilities, it looks like we might have 2 benzene rings, and that is all of our degrees of unsaturation. So, benzylic H's have very messy splitting patterns. You don't get the really nice triplet or really nice doublet that you do get, in the straight chain side of things. So we would even just call these multiplets. You can call anything that's a multiplet is greater than a singlet. Splitting multiple times. So I'm not even going to really make the chart. Sometimes you have a situation, especially where there's a lot of symmetry, that you kind of do a little bit of a guess and check. So I hope it's not too crazy, right? Because we can use our integration numbers as a guide. Because I need to know that I have a benzene ring. So let me just draw that, right? So, and I need 2 of them. Let's just say, what if and actually let me redraw this because I drew it weird. What if I even connected them. Because it seems like I should have I shouldn't have any hydrogens that aren't on a benzene ring. So let's check this, right? Because I would have an H here, an H here, and an H here, right? Because these positions are equivalent, as well as these are, right? All the dots are equal. If I asterisk this position and this position, I can also asterisk this position and this position. And if I put a box around this position, these two would be the same. So just by drawing two benzene rings and connecting them, I can see I actually have 3 unique positions, right? And let's see if the integrations match up. Well, this box position has 2 hydrogens represented. Well, that could be this peak. And, my dot, 4 hydrogens there. There we go. And the asterisk also represents 4. So you may come across a time where you have a spectrum with not many peaks. That's probably because there's a lot of symmetry, right? Because remember, you go through a molecule, and if there's symmetry, those hydrogens are represented on the same peak. And here we happen to have a ton of degrees of unsaturation, and we saw that all of these peaks lied in the possibility of being in a benzylic situation, an aryl situation. Aryl meaning right off the benzene ring. So I just took a guess. I looked at my spectrum. It matched up. Okay, gang. So in this last problem, it'll be a little bit more of a traditional, asymmetric situation. But I just wanted to show you that benzene rings are very common, right? They come in degrees of unsaturation of 4, as well as symmetry can be a thing if you have a very small amount of, signals in your spectrum. Okay, gang, stick with me. Last problem, and then we are officially done with the NMR series. Okay, so we've done this process a few times now, so let's just power on through. Very first thing we do, we look at our molecular formula, we find our degrees of unsaturation. So I'm not going to do the formula, like I've said before, here, because we're just going to, simple scenario, I'm going to ignore oxygen, my degrees of unsaturation then. This formula, if fully saturated, would be C6H14, right? Because 2N plus 2 of 6 would be 14. So you can see I'm missing a pair of hydrogens, right? I'm missing 2. So I have 1 degree of unsaturation. Okay? Cool. Which, like we said, it could be a pi bond, it could be a ring, but maybe that's where the oxygen comes from, right? Just little thoughts that maybe pop up your head as the more experience you get. Alrighty, so let's go through. Let's assign our peaks. So I'm going to call this peak A, peak B, peak C, peak D. Okay. So down here, for peak A, what is my coupling? 1, 2, 3, 4, 5, 6, 7. Okay, it's a septet. Pretty high. So the integration is a 1. My number of neighbors will be 6, right? Because if it's a septet, n plus 1, right? 7. That's how that works. I'm sorry if I'm repeating myself a bunch. Alright, so the appearance. And it looks like we have like a chemical shift. Again, I had to put these in the same between 2 and 3. The chemical shift was really supposed to be like a 2.6, 2.5, somewhere around there. So, if it has 6 neighbors, and we're a little bit more downfield, right? This could be being, if this is our hydrogen right here, we could be next door to a carbonyl. That's in the realm of possibility. So, and you get that from a chemical shift chart that you should have pretty much on you at all times, never leaving your house without it. Just kidding, don't do that. Anyways, bad jokes aside, let's go on to B. B. So coupling, looks like we have a quartet. And integration of 2. So quartet, that means we should have 3 neighbors, because n plus 1. We're a little bit downfield, in the same realm as A. So again, this could be another situation where we are alpha meaning just next door to a carbonyl. So I'm going to list the same type of thing. These guys would hopefully look the same-ish, just different amounts of neighbors. And I'm going to do a chemical shift of about like 2.5. Sorry if my 2's look like Z's. 2. Okay, so now C, I'm just going to put D down there. C, what do we got? We got a doublet. Doublet. That means or integration of 6, right? So this is going to correspond to more than 1 peak, probably 2, 3 integration numbers. And all right, we're a doublet. That means we have 1 neighbor. So if we have 1 neighbor, and integration of 6, we're very close to like a 1.2 or something like that. This is probably going to be, 2 terminal methyl groups of some sort. So probably a CH3 on the end, something like that. Okay, so that was C. Now D. This is something we've seen time and time again. It's a triplet. It's very close to 1. This is going to be your classic terminal methyl group for sure. Integration of 3. We're going to have 2 neighbors. We're going to look just like what we drew above. I'm not going to put the parentheses around because I don't want it makes more of a mess than anything. This is like about, I don't know, like a 0.99, something like that. It's close to 1. Alrighty, so now let's start deducing a structure. I'm going to start off with D. It's super simple, right? Time and time again, we've seen that be a good starting place. Okay? So I'm even going to label it D. You can do this labeling as you draw or not. Sometimes it's helpful. Alright, so D needs to have 2 neighbors. So if I actually put these neighbors right here and continue my chain, not really worrying about where it's going, I then try to find, if I X this out, where's the integration of 2? Well, this could very well be B, right? And remember, B is a quartet, so it has to have 3 neighbors. Well, if we look here and we want to actually make this be a valid, representation of what's on our chart, we actually have our 3 neighbors, which then leads us to the fact that B actually has a chemical shift a little bit downfield. Perfect. We have a degree of unsaturation to use. We did guess the fact that it might look like a carbonyl, so why don't we just plop one on our structure? Great. B is good to go. Everything seems rock solid so far. So now let me continue my chain. Okay. So now let me see if I have anything that's more downfield, right? Because I need to kind of assign this position, or I need to, look at my chart for anything that's more downfield because we are alpha to a carbonyl. Alpha meaning next door. Well, let me find position A, that's septet, right? Because we see that 2.6 chemical shift. That hydrogen would fit pretty well there. And we only have 1 hydrogen, okay? So if I just continue my chain, right, I'd have 2. So I can't have that. Well, remember, we've now used 1, 2, 3, 4 carbons if I don't, continue that. And I have 6. So if I do something like this, 1, 2, 3, 4, 5, 6, right? There are my 2 methyl groups, right there from letter C. I'm left with my 1 hydrogen right there for A. Bingo, bango, bongo. That is the deduced NMR structure. So gang, I hope you see that once you have everything laid out in a chart, it's really just a guess and check and just logically puzzle piece everything together. Like I said before, sometimes this can be frustrating. Sometimes you just do not want to look at another spectrum because you're like, I don't want to, guess and guess and guess, bang my head against the wall, then look at the answer and realize, why didn't I get that right? Well, that's how you get good at this. So lay everything out in the chart, logically kind of start, pick an end if you can identify one, work your way through. You might not get it right on the first try, but you'll continually start to pick up things. You'll see things, very familiar from time and time again from different problems. You'll kind of get just the big picture understanding. Okay, I'm going to provide my practice as well as links to great sites with great practice. So if you have any questions, put them in the comments. Otherwise, we're done with NMR.